Hello, welcome to this second talk in the topology section for the 2022 ICM. I'm Ulrike Tillmann. I'm going to share the session, and I'm very pleased to introduce Nathalie Wahl. She got her PhD 2001 from Oxford, and I'm very proud to say that she has been my student there. She took positions in Northwestern, Aarhus, in Chicago, until in 2006 she ended up in Copenhagen, where she's now the director of the Copenhagen Center for Geometry and Topology. She has had an ERC starter grant and a consolidator grant, and in 2008 she received the Young Elite Researcher Award from the Danish NSF. And in 2016, she was made a member of the Danish Academy of the Natural Sciences. So it's wonderful to have Nathalie presenting her talk on homological stability, a tool for computations, live from Copenhagen.
Thank you for the introduction, and thanks everyone for making this event happen despite the complicated circumstances. So I'll talk about homological stability and thinking of it as a tool for computations. And what I want to start with is a theorem that I proved with Markus Schumich a few years ago. And it says the following: the homology of Thompson's group V is Z when star is equal to 0 and 0 otherwise. And this was answering a question of Brown dating around 92. So what I'll talk about today, I'll be mostly talking about homology of groups, and we'll be using homology of spaces to study homology of groups. Homology is something you could define in other contexts. You could talk about algebras or various other types of homologies than the ones that will show up today. And some of the things I'll talk about do have an analog in these other contexts. And what I'll just say is I'll refer to the article in the proceedings of the Congress, where I do give further references and indications of where else this could go. But some of what I will say today has further generalizations. So what does this theorem has to do with the title? Is here's a sketch of proof. And the proof goes in 2 steps. The first one is a homological stability, which will be to consider the group V as part of a family. So there exists homology isomorphisms from V, which I'll think of V1 in a family of groups, going to a certain group V2, V3, and so on. Okay, so there are such isomorphisms, and in particular, this means that the homology of V is isomorphic to the homology of the limit group V infinity, being the union of all the groups in the sequence along these maps. Okay, so this is the first part of this proof, and then the second says it's a stable computation, which says that the homology of this limit group V infinity is actually isomorphic to the homology of a contractible space. And when we put these things together, 1 + 2, it gives you that the homology of V is isomorphic to the homology of a point, and that is exactly Z when star is 0 and 0 otherwise. Okay, so what I want to do today is give you an idea of how one might come up with such a proof given a group of this sort. And to begin with, I would like to say something about homological stability more generally. Okay, so homological stability, something about a sequence of, in our case, groups. So I have a sequence G1, G2, and so on. And we say they satisfy homological stability if, when you look at the induced maps on homology, Hi Gn to Hi Gn plus 1, this is an isomorphism for all I smaller or equal to some function depending on n, where I want this to be an increasing function of n. Okay, so for example, we could take Gn to be gln R for some ring R, and then a map to gln plus 1 R to take a matrix to the block matrix where I add a 1 in the bottom corner. In this case, so these groups satisfy homological stability, and you can take the function f of n is n minus something called the stable rank of the ring minus 2 over 2. Or another example would be to take Gn is the braid group Bn, which we have already seen in Danny's talk, I guess yesterday sometime. So if I take the braid group on n letters, I can map it to the braid group on n plus 1 letters. How would I do that? If I have a braid, something like this, then I can create a longer braid by just adding the identity on the last letter. Okay, so this would be for the braid groups. In this case, you can take f of n to be n minus 2 over 2, n minus 1 over 2, I think, something like this, n minus 1 over 2. Okay, and maybe one last example is just the one I already mentioned in the proof here. We could take Gn is Vn from before. And in this case, Fn would be infinite for all n. That means, what I mean by this is there will be no range of stability. What we had in the sketch proof of the theorem is that there was always an isomorphism, not just in a range. This is quite unusual. We'll see that this shows up because of some special properties of these groups. Typically, stability ranges look like this, linear bounds. Okay. So I want you to. So let me say this maybe one more time. So homological stability. I sort of said this in my sketch proof already. So for homological stability for a sequence of groups is equivalent to saying that the homology Hi of the group Gn is isomorphic to the homology Hi of the limit group G infinity in the range in the same range as we had before for this function of n. So what I would like you to to have in mind when I say homological stability is to say that this is the same as saying that the homology of Gn resembles more and more the homology of G infinity. And this is what we will call the stable homology. Okay, so that will be how we will think of homological stability. So I want to state 3 facts about homological stability. The first one being that there are lots of examples. So we have already seen a few, the general linear groups, the break groups, these Thompson groups of some form that I will get back to. You could take symmetric groups. You could take symplectic or unitary groups. You could take automorphisms of free groups or various sorts of mapping class groups of manifolds. And here I want to give you a sample theorem that I proved with Alan Hatcher a few years ago. And he says the following: for any 3 manifolds M and N, so you pick 2 3 manifolds. The only condition I want is that the boundary of M is non-empty. Then I can consider the group Gn, which is a mapping class group, so pi naught diff of the manifold obtained by taking M connected sum with N a bunch of times. So this is N times the manifold N, and I'm going to take diffeomorphisms relative to at least some part of the boundary of M, maybe the whole thing, but something lying in M. And so for this group, so having something fixed allows me to define stabilization maps. I will have a map to Gn plus 1 by adding an extra summand and adding the identity diffeomorphism on that summand. And then the theorem says that Hi Gn induced map into Hi Gn plus 1 is an isomorphism for all I smaller or equal to N minus 2 over 2, no dependence on M or N. Okay, so that is the first fact I wanted to give. Here's the second fact. Fact number 2 is that there is a standard proof. So if you want to prove stability, there's a standard way to go. Which is good news. So I'll state a theorem a little bit with slightly vague assumptions. Again, there exist detailed versions of this, but I want you to understand the idea. So this comes from joint work with Oscar Randall Williams and a further improvement by Emanuel Kranich. And he says the following. So if you have groups G1, G2, and so on with compatible maps, from the break groups, I want some map from the break group Bn to my group Gn, compatible in an appropriate way. Then there exists what we call a space of destabilizations Wn for each n, and this has the following property that if I know that the reduced homology of the space is 0 in a range, so for all I smaller or equal to n minus a over k for some fixed k at least 2, so k does not depend on n, and I know this for all n, then stability holds, so hi gn to hi gn plus 1 is an isomorphism in basically the same range, so I strictly smaller than n minus, let's go this up. I think this is this way. Here's a strict one, here's a non-strict inequality, but basically the same range, right? Homological stability happens, and you also get for free a sort of plus a twisted stability statement. So you also have stability with certain twisted coefficients, some that are a form of polynomial coefficients, and some that are a form of abelian coefficients. And in particular for abelian coefficients, it will tell you that stability also automatically holds for the commutator subgroups of the groups. Okay, so this is a statement. Maybe let me say one thing about the space Wn. Wn is a simplicial object, and it's made out of the groups. Wn, the p simplices are simply the group Gn modulo the group Gn minus p minus 1. And then when you have a simplicial object, you need to define face maps. Face maps are defined using the map from the break group. So this is why we need this data. Okay, so now you can look at the theorem and say, what is this theorem saying? This theorem is saying, if I want to know stability, some isomorphism in homology, well, I have to know something else, right? I have to know that a certain space has some vanishing homology. Have I really gained something, right? So we have replaced one statement by another. So now we need what the theorem says is, well, we need or could prove this instead. And so it's over here. So it's reasonable to ask whether this is useful. And so here's at least what I can say. So this theorem, it builds on an old argument of Quillen. And in fact, many, or I really want to say most, stability theorems in this world of that we are in, this context we are in now, so in particular for homology of groups, have been proved using a variant of this. Yeah, a variant of this setup that is maybe not always exactly that space that occurs in the theorem above here, but at least some similar space with similar properties. Okay, so in this sense, at least what I can say is that it tends to be useful and it's worth a try. So if you have a candidate family, it looks like something that fits in the theorem. It has these maps from the braid groups. Maybe that's factors through the symmetric groups. What you see is symmetries, maybe more than braidings. There is this space, I can construct it. It's a simple recipe, and it's worth trying to show it's highly connected. Another remark I wanted to make is there is further work by Galatius, Coopers, and Randall Williams that uses sort of that takes, so what we took here as input is a sequence of groups and this occurrence of the braid groups. What this further work does is it takes as input, in some sense, sort of higher stabilization maps. So considers more ways of stabilizing, and also can get a space out of this higher structure, and gets as output gets statements also past the stable range. So it is possible to do even to get it even a little further. Okay, so that was my my facts number 1 and number 2. I promised. Did I don't know if I promised 3, but I have one more at least. So if we have to use stability for as a method of computation, then we need to know that we can also compute at least the stable homology. So here's my fact number 3, which is maybe more an empirical observation by now, and it says the following. So yeah, the stable homology is often easier to compute. So one thing one can actually say, which is a more of a factual type, is most often, by which I mean under slightly more restrictive assumptions than the ones I have above here in the theorem, what you have is that the homology, this stable homology, so the part of the homology that the groups tend to, they are the homology of what we call an infinite loop space. So this is mathematics going back to the 70s. So let me just say 70s algebraic topology, and again refer to the proceedings for references to the various statements you need here. But you will have a statement of this sort. So the stable homology is that of an infinite loop space. That might not make everybody happy, but it makes some people happy. And so this is like the abelian groups of homotopy theory, and we have tools, other types of tools than the ones. Maybe there are no real tools here. There are lots of tools here to do actual computation. So often we can actually get our hands on these homology groups, and in particular the rational homology is often something that just comes out. Okay, so what I want to do now is to go back to where we started, which is these Higman-Thompson, these Thompson groups, and I will also talk about. I'll do this in a slightly more general context. I'll talk about the groups called the Higman-Thompson groups. So I still owe you, for example, what this sequence of spaces of groups was in this case, and in fact, just to tell you what the Thompson group V is. So I'll do this now. So let's start with Thompson's group V. So V has a subgroup called F, and it's a little bit easier to describe F. So we start with F. F is a subgroup of the homeomorphisms of the intervals. Actually, there will be piecewise linear homeomorphisms. So if I have an interval, and here's a copy of it, and I would like to give you a homeomorphism from the interval to itself, right? And F will be the subgroup of homeomorphisms that are obtained by first subdividing the intervals in a binary manner as many times as I like. So for example, I do something like this, and then on the other side, I will have, say, the same number of subdivisions, and then to get a homeomorphism, what you do is you linearly send the first interval to the first interval, and then the next one to the next one, and so on. Okay, so that's what the group F does. And then V is instead a subgroup of the homeomorphisms of the Cantor set, and it's basically like F, but the difference is that you allow permutations of the sub-intervals. So what we do is we could consider the same intervals here and subdivide them in the same manner. But when I take now my first interval on the left-hand side, I can decide to map it over here instead. Again, linearly, extending linearly. The second one, I could map it here in front, and so on. Okay, so I choose some permutation of the subintervals. So those are the groups F and V, and then the Higman-Thompson groups they have an extra, it's a 2-parameter family of groups, V, J, N, and this is doing the same definitions, but we will take JRE subdivisions of N intervals. So in particular, V is V to 1 because we did binary subdivisions and we had a single interval. Okay, so these are the groups. So the group Vn we will have it's going to be V to N. So let me more in the general case give you the sequence of groups and maps. So when if I fix J, we will just work with a fixed J at a time. I have VJ1, and I'd like to give you a map to VJ2 that will be part of a whole sequence of maps. And what is this map? If I start with a homeomorphism of the Cantor set, so one of these maps in this group that says, okay, you subdivide, binary subdivision somehow, something like this. And then I don't do that, but I give you a permutation, right? This is these groups V. I tell you what to do like this. To get a map of now 2 intervals. So I have 2 intervals here, 2 intervals here, and I'm allowed to subdivide as many times as I want and then permute. Well, I'll do the same thing on the left-hand side, whatever it was. So some strange looking permutation that doesn't look quite right, something like this. And here I'll just take this interval to this interval. Okay, and so I can add further and further intervals and not do, I mean, just extend my map by the identity. Okay, so that is the first piece of data we needed. We needed a sequence of groups. Then we also needed a map from the braid group to the nth group in the sequence, VJN. And what is this doing? Well, if I have a braid, say something like this, so this would be n is equal to 3, then on the other side, I should have a map from 3 intervals to 3 intervals obtained by subdivision and permutations. Well, I'll do no subdivisions, and I will do the permutation that is underlying this braid. So I'll just take this interval to this one to this one, and this one stays what it was. Okay, so it's actually a map that factors through the symmetric groups. Okay, so we have a sequence of groups, and we have maps from the braid groups, and therefore they can be plugged into this recipe for proving homological stability. The recipe said, well, there is a space you can construct, and then you can try to show it is highly connected. So this is what we did. So maybe before I state this, I wanted to say one more thing about the group. So here's a little remark, note. The group VJN is isomorphic to VJN plus J minus 1. This is this little extra property that I mentioned at the beginning. They have a special property of Thompson groups. Why is this? Well, you can think if you have, if I am allowing JRE subdivisions, whenever I have a map from an interval, whenever I try to describe an element here, in some sense I can, I could always say J was 3 here, so I'm subdividing into 3. as soon as I subdivide into 3, at least this looks like 3 intervals going to 3 intervals. Well, it is 3 intervals going to 3 intervals, right? So what this isomorphism is saying is like, well, really, whether you put them side by side or together as one interval doesn't make a difference, right? Because now I'm allowed to subdivide again and again on both sides, right? So these two groups are actually simply isomorphic. Okay. So now let me state the first theorem that we prove with Markus Schumich is that the space Wn that came out of this recipe for proving stability is n-3 connected. So its reduced homology, in particular, vanishes up to the up to that degree. And so, as a corollary, well, Hi, if we apply the theorem Hi v j, so this is for any j. As a corollary, if we apply the theorem, it says Hi v jn to Hi v j n plus 1 is an isomorphism for I smaller or equal to something like n-3 over 2. I'm forced to put an over 2 because I had a condition in the theorem that said that I could only talk about slopes. So I had this k. I have to divide by something which is at least 2. Yes, but now I want to use this little extra fact which says, oh, but by the way, this group Vjn is isomorphic to Vj. I can repeatedly use such isomorphisms. It's isomorphic to Vjn plus r times j minus 1 for any r. I can make what is n in the group, so the rank in the group, I can make it up to isomorphism as big as I like. And so what happens is that in practice, you have to be a little bit careful in this argument, but in practice, the range disappear. I mean, you actually have no range. It is always an isomorphism. Okay, so this was the first part of the proof of the theorem. And then the second part is to say, well, we have to compute now the stable homology. So is the second part, and it says the following: H star of Vj infinity. So it doesn't matter whether I've put infinity, n, or 1 here because they're all isomorphic. But nonetheless, you should think of it as the stable group. I mean, the way we compute it is really in terms of this stable group. Then this is isomorphic to H star of, well, some infinite loop space, something called loop infinity j minus 1, where, so this is what is called the Moore spectrum for z mod j minus 1. So and just to say more precisely what it is the cofiber of a map from the sphere spectrum to itself that multiplies by j minus 1. In particular, we can look at the special case we were interested in at the beginning, which is j is equal to 2. These are the binary subdivisions. When you put j is equal to 2 over here, well, j minus 1 is 1. This map is the identity map. Taking the cofiber, it's sort of killing this map. We're killing the identity map. We kill the space. Okay. So in this case, we get M1, which is a trivial spectrum, and in particular, its infinite loop space is just a contractible space, right? So we get the homology of V, so this is the end, the end of the proof, we'll say this, where the homology of the group V we were interested in is isomorphic to the homology of V to infinity. This was the stability statement. This is isomorphic to the homology of loop infinity M1, but this is a trivial this is a contractible space. And so we get this Z in dimension 0 and 0 otherwise. Okay. So to finish, I would like to say a little bit about how one might guess the occurrence of this Moore spectrum. Maybe also say a word about a corollary. Maybe I start with the corollary, and then we can do the Moore spectrum. So, for example, easy consequences. I said these infinite loop spaces are in many cases they're often easier to compute. So it's often easier to compute their homology. So, for example, one immediately gets out of this description that the rational homology of the groups is trivial. So reduce, it's 0. So this is for all J and N. And another computation you can make is we saw the homology when J is equal to 2. There is no homology at all. Also integrally, if you put J is bigger or equal to 3, then there is homology actually. And what we can show is if you take the homology in degree 2p minus 3 of I'm going to screw this up. Of when I'm screwing, yeah, of V. I think I'm sorry. I think I want to put p plus 1 here. N is this is J. I'm screwing this up. I'm sorry. It's Z mod P. So in for some appropriate thing over here. I'm sorry. Look it up in the paper. So you will get. I mean, you will get what I wanted to say is you will get 0 up to a certain stage, and then you get a first non-trivial homology group, which will be a finite group. The rational homology being trivial. Okay, so I wanted to finish by what is the idea of why should these Moore spectra show up, and so Thomas gave us this description of the sphere spectrum as you should think of the numbers 1, 2, 3, and so on. They're like slightly fuzzy, but maybe one in what I want to describe, 1 won't be fuzzy. I know it should be in some sense, but so far you should think of somehow the sphere spectrum. It has something to do with taking the numbers. So the numbers which you can think of as finite sets, if you like, with their permutations. So their isomorphisms with the permutations thought of as the isomorphisms of finite sets. And what we see when we study the groups V, J, N for, let's say, for all N, then what we're looking at is also finite sets, where I'm thinking of the sets as being the intervals I talked about, and with their permutations, we also had permutations of the intervals, but now we made this identification that one interval was equivalent to J intervals, or in this setup, 0 is equivalent to J minus 1. which is what happens when we did our co-fiber earlier. I'll stop here.
Thank you very much, Nathalie. That was great, beautiful talk. And if you have not seen it yet, Nathalie mentioned it, and there's a preprint on the archive already.